Let n be a positive integer. Find the smallest integer k with this following property. Given any real numbers a1 through ad with some n, and each one is between 0 and 1 inclusive, it's possible to partition these numbers into k groups, which may or may not be empty, such that the sum of the numbers in each group is at most 1. So let's start off slow. We're going to start off with the smallest positive integer n, which is n equals 1. Then we just have that a1 plus all the way to plus ad is equal to 1. And we can just place everything into one group. So that gives k is equal to 1. Now n equals 2 is slightly more difficult because we have a1 plus all the way to plus ad is equal to 2. And now we can take a look at what the value of d is. So if d is equal to 1, then that just means that the sum is a1 is equal to 2, and that violates the problem condition. If d is equal to 2, then we have that a1 plus a2 is equal to 2, and since they are both at most 1, this implies that each is 1. And then we have to place each in our own group. So that means that k is at least 2. Now what happens when k is equal to 3? Because then a1 plus a2 plus a3 is equal to 2. And the most natural case here is to make all the numbers equal. And that makes it 2/3, 2/3, and 2/3. And if we try putting them into two groups, two of them must be in the same group. But then the sum is then equal to 4/3, which is greater than 1. And that's bad. So therefore, each one must go inside its own group, which means that k is greater than or equal to 3 in this case. And now if we have 4 numbers, we have a1 plus a2 plus a3 plus a4 is equal to 2. Making the numbers equal won't do anything because each number is just equal to 1/2. And we can just pair up the numbers as follows. So that won't work. So that makes us think that k equals 3 is the best for n equals 2. We'll get back to that later. So for now, let's go to n equals 3. So we now have a1 all the way to plus a d is equal to 3. And clearly d is at least 3 because otherwise the numbers are greater than 1. And d equals 3 makes all the numbers equal to 1, and that's a boring case. So let's try making all the numbers, let's set d equal to 4. So then we have a1 plus a2 plus a3 plus a4 is equal to 3. And we can do the same trick of setting the numbers equal to get 3/4, 3/4, 3/4, and 3/4. And combining any two will make the sum greater than 1. So k is at least 4. And 4 is really small, and it's actually not the smallest one number that makes this trick work. Not the largest, I meant. Because this trick also works when we have 5 numbers, when d equals 5. Because we can also make it 3/5, 3/5, 3/5, 3/5, and 3/5. That will also give 3. But each one must go inside its own group because otherwise the sum is 6/5, which is greater than 1. And so for n equals 3, we have k is greater than or equal to 5. And this is the furthest we can go because when we get to 6, we just get the 1/2 case again. So this makes us believe that our answer is equal to k is equal to 2n minus 1. Because it follows the odd number pattern as we see here. So how do we prove that k equals 2n minus 1 groups are necessary. In other words, how do we prove that we cannot use less groups? Well, we can rigorize this idea of making all the numbers equal for as long as we can. Here's how. So we have that a1 plus all the way to plus ad is equal to n, and each of these guys is n over d, and so on all the way to n over d. And so long as 2n over d is greater than 1, we are fine. And this equates to d is less than 2n, and then which is d is less than or equal to 2n minus 1. And so if we consider the numbers n over 2n minus 1 all the way to n over 2n minus 1, the sum of any two of them is 2n over 2n minus 1, which is greater than 1. So each one must go in its own group, implying that k is greater than or equal to 2n minus 1. Now that we have shown that k is greater than or equal to 2n minus 1, we are going to prove that we can always achieve this task when k is equal to 2n minus 1. So first of all, if d is less than or equal to 2n minus 1, the construction is clear. Just put each number in its own group and let the spare groups be empty, because d is less than or equal to k. So now our real focus is when d is greater than k. And the first issue is when a1 plus a2 plus all the way to plus a2n is equal to n. And we want to combine two of the numbers inside some group somehow. Because otherwise, if we can't do that, then k will be greater than or equal to 2n, and not 2n minus 1. So let's see if we can combine two numbers in a group. Suppose for the sake of contradiction that we can't do this. Then we always have that a1 plus a2 is greater than or equal to 1. And similarly, like a1 plus a3 is greater than or equal to 1, and so on and so forth, for every single pair of the AIs. So like AI plus AJ is greater than or equal to 1. Or it should be greater than 1. Because it can be at most 1. So let's see what happens when we sum all these guys up. I'll go ahead and remark later that you do not need to sum all of these guys up, but it's more motivated and natural if you sum everything up. So whenever you sum all pairs of these guys up, where I is less than j, a1 appears 2n minus 1 times because it is part of a1 plus a2, a1 plus a3, and so on. So it's 2n minus 1 times a1, and by symmetry, a2 also appears 2n minus 1 times. So it just becomes 2n minus 1 times a1 plus a2 plus all the way to plus an, 2n. And this is greater than or equal to 2n minus 1 times n. This is what it's equal to. And it's greater than, because we're summing all of these guys up, 2n choose 2. But as we have it, 2n choose 2 is just 2n times 2n minus 1 over 2, which is n times 2n minus 1. So n times 2n minus 1 is greater than n times 2n minus 1. And that's a contradiction. Therefore, one of these guys here is less than or equal to 1, and we can combine them. And what happens when we combine them here? We get one less number to think about, because we can just cluster them together. For example, we can consider a1 plus a2 plus a3 plus a4 plus so on to a2k is equal, or 2n is equal to n. And we can treat this as one number, this as the second, and so on to the 2n minus 1. And we can apply the construction for 2n minus 1. And does this work when we have 2n only? No, we can continue this process and go downwards. sort of like an induction in that sense. And therefore, by continuing this downward until we get all the way to k equals 2n minus 1, at which point we can just put each number in its own group, we solve the problem for k equals 2n minus 1. Therefore, since we prove that k is greater than or equal to 2n minus 1 by finding an explicit construction, and then we prove that we can always achieve the task when k is equal to 2n minus 1, this implies that the answer to our problem is k is equal to 2n minus 1. Thank you so much for watching this video. Please subscribe if you'd like to see more.